Hello guys, this is a video about PULsE, the processing unit for laser flash experiments, and in this video I'm going to show you the capabilities of model selection, and we're going to delve deeper into the experimental set of data that we touched upon last time when we were looking at the Pyrus RAM sample that was measured with an edge instrument. And as you might recall, there was a slight problem with the data because the distribution of residuals seemed slightly abnormal, which is visualized, for example, for this curve taken at 600 degrees C. So if we plot the distribution of residuals, we can see that there's a small shift of this plot towards the right, so there's a slight bias in the model selection. This means that most likely this model is not ideal for that specific case, and I'm going to tell you more about why this actually happened. But before we start, I actually wanted to share with you that there have been some changes to PULsE, including the user interface, as you see here. So I think it has become better, in my opinion, because it's easier to navigate across the different menus and the different tabs and so on. And it's also better for the eye because it doesn't strain you to look at the dark colors, in my opinion. And of course there have been some changes to the functionality. So for example, the model statements have been slightly adjusted, and you might also see that there's a very interesting feature that has been introduced. This is called the graphical lock, and this has been introduced just maybe a month ago or something like that, and it allows you to see in real time the progress with your current task. And this graphical locks are saved for each of the tasks that have been processed, and you can switch back to the usual text mode by clicking on this checkbox and back to the graphical menu. And also I've made some improvements on the performance, of course, of the tasks, and now I think it runs much better. By the way, if you wish to see the list of changes that have been committed since the last release, you can navigate to the PULsE website, which is accessible from the main menu in the software, and then click on the, for example, the current version 1.98, and then there's a brief description of the changes. So for example, in this version specifically, I added the save and load session buttons, which are available on the PULsE main menu when clicking on file, and then there are now two menu items for saving and loading sessions, which is extremely useful because you can actually save your current progress, then switch off your laptop, then you can exit PULsE, and in a week or maybe in 2 weeks you can switch back to the same session by clicking on the load session button, and it will be, all information will be right there. So it wasn't available until recently. And there are also some other changes that have been introduced in a previous release. So since the last video there had been quite a few releases here. So one of them was released in January 11, January 9th, and yes, so for example, this graphical login thing has been introduced in PULsE 1.97b. There are also some issues with PULsE discretization which had been fixed, and now you shouldn't run into any issues with the PULsE discretization regardless of the length of the real experiment. And yeah, you can also see the changes to the sources themselves, so they are also available here on GitHub. and if you know Java, then you are able to see the changes for yourself. So this is not a secret at all. Let's get back to the software screen. Because we will be comparing different models, it's best to save the current results, for example, to a CSV file by clicking on this button on the bottom right. And then we will just save it in a folder so that we can examine it later. I will just add a file named pyro1 with the current results. And for example, if you open that folder now, you can use GNU-plot as we did last time in the last video, and then we can plot the thermal diffusivity here, which is the second and the third column. So I'm just going to type pyro using 2 and 3. And so that's the thermal diffusivity. I'll just make it slightly more visually appealing by multiplying the second column by 1 million. And there you go. So that's in millimeters square per second thermal diffusivity. That's the one-dimensional problem. Now, getting back to the model selection. So as you remember, previously we have selected this classical 1D model, which only accounts for the actual heat fluxes. And this is not always the best case, especially when you have thick samples and when you suspect that radial heat fluxes may occur. In that case, it's better to use the two-dimensional model, which is also selectable from the list on the left. So I'm going to select the two-dimensional model, and the calculation curve will change because a different model has been selected, and it will reset the properties. For example, the thermal diffusivity, if I remember correctly, it resets it to some initial approximation. So because we had this apply to all tasks checkbox enabled, we will have changed the model for each of these tasks, and you can see that the solution is still not optimized, so we need to search for a different solution. Again, we just choose the Levenberg-Marquardt optimizer, and in this case we actually have an option to include different parameters. If you remember, last time we only had one parameter for the heat loss, which is BIF, the bio number for the actual heat losses. And in the two-dimensional case, we can choose either from having two parameters for the heat losses, one for the side surfaces and the other for the faces, or to have one combined parameter. In this case, this kind of reduces the number of parameters for the problem, so that we can still retain the low number of parameters characteristic to a more simple model, but use the additional geometrical considerations that may be included in the two-dimensional model, such as the variable laser spot diameter, the variable field of view, etc. Again, in case of the two-dimensional model, we actually take these parameters explicitly into account. And if you have on the PULsE 2D property, you will be able to see that it actually accounts for the exact spot diameter, which is loaded from the file, and also it accounts for the exact field of view. If you click on the sample thermal physical properties 2D, then you will see that the field of view is also set to the value that has been specified in the file specifically for that task. So now I'm going to repeat the measurements for the two-dimensional model by simply clicking this green man button. And once again, the problems are being executed. They have been queued for execution, and because we're using a more sophisticated model and one that requires more computational time, it obviously takes more time to finish. And in this case, we can, for example, see the current progress by either looking at the search statistic or by, yes, so for example, here we can see in real time how the parameters change, and this dashed line for each of the parameter indicates the convergence of that parameter, and once a certain level of convergence has been reached, the task is deemed finished. So we will just wait until it all finishes. It takes a while. Now the calculations have definitely been finished, and I want to examine the results. And first thing that I'm going to examine is the search statistic. If you remember, last calculation resulted in a search statistic as low as, or to be speaking correctly, as high as 1.5 times 10 to the minus 3. So I need to see if this is still the case here. So the lowest search statistic is 5.5 times 10 to the minus 5, and the highest, okay, so it's still 1.29 times 10 to the minus 3. So this is likely because of the outliers again that are included in the search. You can always exclude this part by just dragging this dashed line to the desired location, so that sets the actual range for the measurement. But I actually want to see something different. I want to see the distribution. Has the distribution of the bulk of the residuals actually changed? And I'm going to zoom in on the central region for the residuals, increase the number of bins again, and here I actually see that in comparison to the previous result, the mean value for that histogram is actually much closer to 0. So that means that regardless of the fact that we have outliers for that specific curve, the mean value for that histogram is still very close to 0. If we, of course, take into account only this central region. Now, this likely means that we have a much better representation of the, let's say, truth in this calculation. So obviously the value of the thermal diffusivity should also have changed. And how can we check this? You can do this by directly comparing the current results that are displayed in this table here with the old results. And I'm going to save them again to a file named pyro2 because it's easier to compare in GNU-plot. And basically I now have 2 files in the same folder, and I'm just going to compare the results, the results that have been listed in the table. So once again I do the same procedure, but just for 2 files instead of 1, and now I can see that the results for that second run, which are indicated by these green crosses, are actually higher than in the last calculation for the one-dimensional case. And what does this actually mean? This means that the table has been populated by a new set of results. But how do you know that the results that have been obtained last time are actually worse than the results that we have gotten this time? The answer to that question is actually easier than you think. If you untick the graphical log here in that checkbox down there, you will be able to see that the text log says that the new results are actually better than those previously obtained. So this means that the result that you currently see in the table here is the one corresponding to the second calculation run. And you can actually check how those results that had been previously obtained and the new set of results compare to each other. If you right-click on a task, you can access the stored calculations by clicking on this menu item. And here you're able to see that there are two stored calculations corresponding to two finished runs of this task, and the two-dimensional model that has been used to produce the second set of results yields an optimizer statistic which is lower, and also quite importantly, the model selection statistic is also lower in that case. And there is also a quantity which is called the omega, or the statistical weight, which indicates the probability of selecting a specific model as the best model. So if you compare the actual curves for those models for the 1D and the 2D, you will see that the differences look very subtle. But actually, as you have just seen, there are some significant differences in the thermal diffusivity values for those two specific runs. And obviously you need a reliable quantity or reliable means of telling whether the result that has been currently obtained is better or worse than the previous one. And for that specific task, you have the model selection criteria. Right now the BIC statistic is selected. There is also an option to use the AIC statistic, and you can also recalculate the statistical weights if you choose a different selection criterion by pressing on this button. And here you still see that even with the AIC statistic, the model of choice will still be the two-dimensional, specifically for that task that corresponds to a temperature of 600 degrees C. So again, there are model selection criteria based on the AIC and BIC statistics. You can look those up in Wikipedia for a brief description of what they do. So basically, in addition to including the optimizer statistic, in this case the sum of squared residuals, these statistics also have an additional penalizing term, which is responsible for a bias towards models with a lower number of parameters. Ideally, you want a model that has the lowest number of parameters possible, and those BIC and AIC statistics represent the end means of doing this comparison, which is in accordance to the statistical theory. And in addition to the BIC and AIC, which act for models that can be independent of each other. So for example, if you want to compare let's say a transparent model and a two-dimensional model, you can still do the comparison with the BIC and AIC. But there is actually also another way of telling whether a model is better or not. This is the F test, which stands for the Fisher test. But this Fisher test only works for nested models. So in case that we have here, the one-dimensional model is actually a special case of the two-dimensional model, where you set the side heat losses to 0, and also the whole face of the cylinder is completely covered with the laser pulse. And it can be strictly shown that in that case, and in that case only, the solution of those two models actually overlaps. And obviously, if you have conditions which say that you don't have very active heat losses, such as at low temperatures, then obviously the model of choice would be let's say the one that doesn't have so much parameters that can influence the solution. But this Fisher test, it actually represents something that works for nested models. So for that specific case, when the one-dimensional model is actually a special case of the more general two-dimensional model. And this Fisher test is done in background, and the line that you see here that says better or worse calculations than previously obtained is actually based on that Fisher test. However, this Fisher test is invoked only in case if the stored calculations contain only nested models. But in general, of course, the BAC or AIC will automatically be invoked to select the best model of the available calculations at this time. Now, if we look at the different curves, so for example, the one at 25 degrees C, which has a much lower value of the heat losses, looking at the stored calculations reveals that the the one-dimensional and the two-dimensional models both have a parameter count of an optimizer statistic of 4 times 10 to the minus 4, but the model selection statistic is different, and it's lower in case of the one-dimensional model, and also the statistical weight is also lower. In that case, this means that there is not much difference between choosing a 3-parameter or 4-parameter model. And if you now look back at the graph for the thermal diffusivity at different temperatures, you will see that the maximum discrepancy between the models is observed at high temperatures, while the low temperature value at 298 Kelvin or 25 degrees C corresponds to negligible differences between these models. And this is directly reflected in the fact that they both produce the same optimizer statistic, but the one that has fewer parameters is of course preferred. Now that's it basically. So you have the results that correspond to the best available model for each specific task, and again you can choose to have to display the average results, and then you get some values that you can later compare with the literature values. And analysis reveals that comparing those values to literature yields very good agreement between the currently calculated values and the literature values. So that means that you have successfully done your job at processing data with the PULsE software for the Pyrus RAM with 3mm thickness. In the next video, I'm going to tell you about the implications that the complex pulse shape has on samples with small thickness. In that case, the actual shape of the pulse matters very much if you are really interested in precise calculations of the thermal diffusivity. But this is just a matter for a future video. And now, if you want to save this result, you can save this session, for example, as Pyro 3mm. And after a while, this has been saved, and then you can, for example, choose to clean this up, and then at any time you can load this again. So that's it. Thank you for watching.